Welcome class, it's Miss Brown and today we're talking about projectile motion. Alright, so what I'd like you to do is I'd like you to use this worksheet to follow along in the notes. It says Unit 3, Kinematics in 2D, 3, Projectile Motions Type 1 and Type 2. So follow along. The parts that are in green are the parts you're going to need to write down. So let's start about this. I want you to remember from the past, that a projectile is an object that moves through the air and the only force on it is gravity. So here is my physics sphere. Here is a projectile moving through the air. It has no engine, no wings. It's not a golden snitch. It's not going to push itself on its own. The only force on it after I let go is the force that's pulling it down, the force of gravity. So far we've only talked about one-dimensional projectiles. Ones that are dropped, free fall, ones that maybe have initial vertical velocity, and maybe even ones that have initial negative velocity. They get thrown down. So today, we're going to open it up. We're going to think about two dimensions. We're going to talk about two-dimensional projectile. So let's move on. There are three types that we're going to talk about. The notes sort of implied this, the title of them. So that's a little easier to read. Okay, so the type 1 is going to be a projectile which is launched horizontally. So this person is standing on top of a cliff, on top of a building, on top of a ladder, and they're going to shoot it horizontally, and it'll go down eventually. Or you can have the situation here, it's a cannon, this type 2. We're going to launch it at an angle. So that's when you get the nice arc, when you launch it at an angle. But then in the type 2, you're going to land at the same height where you shot the ball. So that makes the math a little bit easier. Type 3 is where we pull it all together. We flex all our physics muscles. We do from a height, landing lower, or maybe landing higher, and we're shooting at an angle. So we need trigonometry, and we need all sorts of algebra. So today we're just going to start with type 1, and if we have time, we're going to do type 2, but I'll see how long this video is because it might get long. Now this is a complicated topic. This might be something you struggle with. This is why I chose this topic for my video lesson. So you can come back and rewatch the parts you want as many times as you want. And if you hate the way I explain it, go look at Khan Academy. Look at Flipping Physics is another YouTube channel that looks pretty good. I haven't watched all those videos yet. Read the Physics Classroom. Whatever works for you, do that. Bozeman Science probably has videos too. If you don't like me or my voice, listen to some other person. All right, here we go. I want you to recall from yesterday, or the last lesson, that perpendicular vectors are completely independent. Remember when we drove our car across the river made of the whiteboard? No matter how fast we move the whiteboard, the car got across in the same time. And no matter how fast the river flows, it's going to take the same time for a boat to get across if it's given a certain velocity across the river because of its engine. Now, here's the part that's written in green. Oh, you can't read that. Great. This is the part you need to read down. Remember, the x and the y components are perpendicular. So the x component of our flight, the part that's to the side, and the y component, the part that's going up and down, they're perpendicular. And therefore, they're completely independent. We're going to have to treat these separately. We're going to have to do the math in a way where they're separate. Oh well, it'll be fun. Anyway, here we go. I want you to go to the part on your paper where it says x components. So after I let go of this ball, no matter what I do to it, I'm putting a force with my hand in, but once I let go, there's no net force on the ball in the x direction. Nothing's pushing it this way. It doesn't have an engine. Nothing's pushing it this way. Noah, we're pretending there's no air resistance. I know. All right, but at this slow speed for the small object, we can assume there's no air resistance. So, because there's no net force working on the projectile in the x direction, the acceleration is always 0. So write that down. Next, what equations can we use for things that are moving with no acceleration? I'm glad you asked. Here we go. We can use the v equals displacement divided by time equation. And we can use the xf equals xi plus the velocity times the time. Notice How for the velocity, I'm using an x subscript. Because this object is going to have an x velocity and a y velocity. It's moving this way, but it also starts going this way, and then it turns around and goes that way. So I'm going to need to be very careful with these subscripts so I know what on God's green earth I'm talking about. All right. Now, let's move to this part here where it says the y component. So, in the y direction, there's always a constant acceleration. What direction is that acceleration? Looks down to me. So that constant acceleration is down. And how much is it accelerating? Negative 9.8. G, the gravitational field strength on Earth. Let's write it down. And what's the unit for acceleration? Meters per second squared. All right, because of this, we need to use the equations which have acceleration in them. But be careful, first of all, switch x to y and put a little subscript on my v so I know the difference between how it's moving this way versus how it's moving up and then down. So the y velocity is going to change. I'm jumping ahead of myself. I do that. All right, moving on. Here are the equations we can use. It's not xf equals xi anymore. It's yf equals yi plus the y velocity, initial, times the time, plus 1/2 times the acceleration times the time squared. This is that same long equation we used before, but I'm just saying we can only use it in the y direction. So I'll put y's here. All right, what else can we use? We can use this equation. The same no time equation. If we ever don't care about the time, this is the equation we would use. Additionally, we can use the good old short Vy equals the V final equals the initial plus the acceleration times time. But again, I put these extra subscripts. They might seem tedious. I know they do NOAA, but they're going to save your butt at some point in time, and then you'll say thank you when you're in NC State engineering program, okay? Thank you. Moving on. So, there's one more thing we need to get into before we do an example problem. Right here, it says, what is the only value that we can use in on both sides, on the x and on the y? So let's look. If we look at these equations in green, what do they both have? There's only one thing they both have, and that's time. So here we go. The only value that could ever be used on both sides in a two-dimensional projectile motion problem is, you got it, time. And this is because time is a scalar. Time doesn't care which direction you're going. It's going to keep on going forward until you're old like me. All right, make sure you write that down. You got it? All right, let's go. So here we go. Now it's the time we've all been waiting for. It's the example problem. We're going to do example problem for type 1 right here. So, a student. You cannot see that. So a student sits on the roof of their house, which is 12 meters high. She's launching water balloons. I don't know why. And from a slingshot at 14 meters per second. And if she fires a water balloon directly horizontally, how long will it be airborne? That means how long will it be in the air before it hits the ground? And how far, what distance will it travel? So let's draw a picture. Always draw a picture. So here we go. Here is her house. It has a flat roof for some reason, and it is 12 meters high. She's standing on top. And she launches this air balloon, this water balloon, completely horizontally. So eventually, it's going to go, even though she's launching it horizontally, it's going to fall downwards. And it's eventually going to hit the ground. So the question is, how long? You can draw that picture really small right here, but I just had to flex my art muscles. The first question is, how long will it be airborne? What are we looking for? How long? It's not a distance, it's a time. So, what does this depend on? Does this depend on the x speed? So if it's going like this and we forgot completely about the acceleration down, will it ever hit the ground? No. Because there's no acceleration in the x direction. It's not, as far as it goes to the side, it's not going to hit the ground. We care about the y direction. We care about gravity pulling it down. So this is going to depend only on that y direction. All right. So let me look at how I did this last. We have to treat these things completely separately, x and y. That's what we meant by independence of perpendicular vectors yesterday. So let me write it down. I'm just going to think only about the y direction. Sometimes when it's lazy, I'll just write y dir. You can do that too, if you want to save space on your paper. Okay, so what do we know in this problem about the y direction? So, let's think. So what's the acceleration in the y direction? Some of you may know that. Negative 9.8, just like every falling object. So what's the initial position in the y direction? I'm going to call the ground 0. So the initial position in the y direction is the height of her roof, which was 12 meters. So y initial is 12. Okay, and the y final, with the end time we care about, when it hits the ground. So how high is it when it's on the ground? 0. So y final, that's 0. So let's think. We know the acceleration. We know y initial. We know y final. What's the initial velocity in the y direction? So if she shoots it completely horizontally, that initial velocity is some number in the x direction. But if it's completely horizontal, it's not moving up at all. It's not moving down at all. So that y component of that initial velocity is 0. I forgot my units. All right. So it looks like we have a lot of numbers about y right here. So what I'm going to need to do is I'm going to need the long equation. So here we go. You should have this written down somewhere on your paper already. So the long equation that we're going to use is going to be y final equals y initial plus v initial t plus 1/2 a t squared. Oh, do we really have to do that? Oh, there's a trick. Thank you. So let's plug in as many numbers as we can. The final y is 0 from here. The initial y was 12 plus the initial velocity was 0, but 0 times t, no matter what time it is, any number times 0, you know the rep, always equals 0. So here we go. That's 0. So sometimes we'll draw an arrow through something, and right, it goes to 0. That's what that means for me. So plus 1/2 times a, what's my acceleration? Negative 9.8. Times t squared. All right. So I have an equation, and I think I can solve for t. Good. Let me see what I got. I'm going to multiply these things together. 0 stays 0, 12 stays 12, plus 0, I don't need to write that, plus 1/2 times 9.8, it's negative 9.8, so it's a negative 4.9 t squared. All right, I'm trying to solve for t because, oh, why am I doing that? I never told you. We need to solve for time because I'm trying to figure out how long it's going to be airborne, how long it's going to be in the air, how much time it's going to be in the air. So I'm solving for the time. Excellent. So, okay, I need to get this t by itself. So first, let's get it on the other side, away from the 12. Then let's get rid of this pesky 4.9 by dividing both sides by 4.9. So those cancel, they go to 1. Oh, it's negative, so let's put a negative on this side. Let's multiply it by -1, both sides. Good. Now I have t squared is equal to 12 divided by 4.9. Let's get that. Don't fall asleep, computer. This is exciting. So that gives me last year I did the math wrong, so let me get a calculator. You guys probably already did this. All right, 12 divided by 4.9 equal 2.448. How many sig figs do we have? It's like 2 sig figs. Maybe, yeah, 2. So let's go 2.4. Mm, 2.44. All right, now I have t squared is 2.45. So to undo that squared, every function has an undo. The undo of squared is square root. So let's square root both sides. So therefore, t is the square root of 2.45 is 1.56, but with only 2 sig figs, let's call it 1.6 seconds. Check in your calculators if I'm right. If I'm wrong, tell me tomorrow. Okay, so I have the time. Is this the answer? What was I looking for? I never wrote what I was trying to find. This is why Miss Brown always goes. All right, find t is what it said, how much time. Good. Time is 1.6 seconds. All right, we got the answer to part A. Feeling like a boss. All right, moving on. Oh, this is too long of a video. Anyway, now part B says how far forward. So she's shooting it. Oh, she's on this way in the picture. How far forward will it travel? So how far dx will it go? So we're asking really about delta x. That's from where she launched it to where it hits the ground. So now I have to treat the x direction completely separately. There's only one thing that can transfer from y to x, and I wrote, and the only thing that can transfer is the time, because time is the only scalar in this problem. Everything else has direction. Anyway, all right, let's do the x. So here we go. Same problem. And if you ever need to pause it and go back and rewrite something, you could do that. So I know the time is 1.6 seconds. Now I'm going to do the x direction. Let's think about what I know about the x direction. I know x initial is 0. I know Vx equals 14. And the acceleration in the x direction, what's that? It's nothing. It's 0 because there's no force. After she lets go of it, no force. So the acceleration is 0. So let's look back at those x equations I said I could use. I'm going to find the change in x. Ooh. All right, so we had Vx equals change in x over t. Let's multiply both sides by t. So the change in x equals Vx times the time. All right, so that's what I'm solving for. Thank goodness. Let's plug in 14 and 1.6 in here. And last time that got me 22.4 meters. Oh, I should put my, so what else? How many sig figs is that? Oh, my computer died. Hope you can still see me. So, how many sig figs is that? That's 3, but how many was in the problem? 3, 2. Looks like I only need 2 sig figs for my answer. So that's 22 meters. There we go. And that is just one incredibly simple 2D predictor. Well, simple is the wrong word. They're not going to get much easier than this. That's what I'm saying. So, with this information, what I'd like you to do, review that, think about it, come up with what's confusing you, come up with your points of confusion. And I want you to try, give your good old high school try to example about the color supreme. It's the same idea where something is moving off a cliff and coming down. Let's see what you can figure out. All right, I appreciate you. Thank you for working hard. We choose physics, not because it's easy, but because it is hard. And the master has failed more times than the beginner has even tried. So keep on trying. Thank you.